Welcome back to Integral Calculus. In this video, I want to introduce you to some formulas for calculating surface area of solids of revolution. We've established previously the idea of a solid of revolution. The analogy that I like to use is the result of something like wood turning on a lathe. If you trace out a pattern, that gives you a two-dimensional curve, and then if you push that pattern into a workpiece that is turning about a lathe, it rotates the pattern around and gives you a three-dimensional result. Calculating the volume is something we've already established, and now we want to look at surface area. Before we get into this, I do want to stress that there are two meanings of the phrase surface area. The total surface area, which we generally represent using a capital A, and the lateral surface area, which we generally represent using a capital S. I'm going to use a right circular cylinder as an example. This is a formula that you probably already know, although it may or may not be top of mind knowledge. The total surface area of a right circular cylinder, which has some radius and some height, is 2 pi r squared plus 2 pi r h. And the lateral surface area is 2 pi r h. So what's different? Well, in the total surface area, we have an extra term, 2 pi r squared. And, well, that looks somewhat familiar. Pi r squared is the area of a circle. And, well, there's a circle. And sitting down at the bottom of the can, there's another circle. The areas of both of those circles are pi r squared. There are two of them, hence 2 pi r squared. And then the remaining is the side. Right, so the area of the side of the cylinder is 2 pi r h. That's what we refer to when we're talking about the lateral surface area. And it is lateral surface area that we're going to be calculating here. Much like I've done with the volume, I'm going to use the formula from a cylinder as my basis for a solid of revolution. Because the difference between a cylinder and a solid of revolution is that my radius is now a function of distance along my height. One thing that you do have to pay attention to, make sure that you're using a capital S here. I am greatly exaggerating this capital S, but capital S is a surface area. Lowercase s is, lowercase s is an arc length. Although when you look at this formula, you might not be surprised that we're going to have the integral of 2 pi times r as a function of x, and not times dx, but rather times d little s, where little s is the arc length parameter. Right, so my function r, speaking more generally, is going to be our function f of x, and then looking back at our previous study of arc length, ds is the square root of 1 plus f prime of x squared dx. All right, so this is the formula for the lateral surface area of an arbitrary shape. It can be intimidating, right? Honestly, it kind of looks a little bit frightening. But all told, it's not that bad. It's not usually as bad as even the arc length formula alone, even though it packs more punch. The fact that there's an f of x outside of the square root very often means that we're going to have something that we can use as a u substitution, and the integration isn't necessarily going to be challenging. As an example, I'm going to go through a relatively simple problem. This is a formula that you may have encountered in the past. Yeah, that's a straight line. And if you take that straight line and rotate it about the x-axis, come on, that's close enough, you get a cone. And the formula for the surface area of a cone is quite annoying. Although, let me see if I can do this. I'm not sure if this is going to work or not. Nope, not going to work. That's okay. I was going to try to reorient it because going in the other direction is actually going to be a little bit easier. All right, so I'm just going to flip this cone around so that it goes through the point 0, 0, and the point HR. Right, so the x-coordinate is the height of the cone, the y-coordinate is the radius of the cone, and the line there is going to be, well, the slope is r minus 0, which is r, h minus 0, which is h, times x. That is a very easy slope to deal with. All right, so we're going to try to find the surface area for y equals r over h x between x equals 0 and x equals h. And yes, I'm going to do this for variables without throwing any numbers in whatsoever because I'm a glutton for punishment. All right, so I'm going to need the derivative. The derivative here is fairly simple. It's just going to be r over h. And then from there, I can get that the surface area is going to be the integral from 0 to h of 2 pi times r over h x times the square root of 1 plus r over h times dx. And yeah, there's a lot of constants there that we can just get rid of. So the 2, the pi, the r, the h, and even the square root of 1 plus r over h all come out of the integral. And we're really just left with the integral from 0 to h of x dx. So we'll have 1/2 x squared between 0 and h, which is going to give us a 1/2 h squared. The 2 and the 1/2 are going to cancel each other out. The h down here is going to cancel out one of those h's. And we end up with pi times r times h times the square root of 1 plus r over h. And that's usually how I see the formula, although every now and then I will see people try to rearrange this and make it look nicer in some way or another. But something in that general idea is what we're looking at. As with the formula for volume, working with surface area, there's a lot of complication that you can introduce by rotating about things other than the x-axis. But if you take the time to set up your problem correctly, you can always rephrase it as integration about the x-axis, and that's what we're going to do here. Write an integral to calculate the surface area of the curve f of x equals the square root of x, rotated about the x-axis between x equals 1 and x equals 4. So as with other videos in this part of the lecture, write an integral. I don't necessarily expect you to evaluate the integral. If you want to, go ahead. I think this one is fairly doable. But take a couple of minutes, see where you can get with that, and I'll see you in the next video.